Hey everyone, and welcome back to Gorilla Suit's Redstone Mechanics tutorials. In this video we're going to go over logic gates and just logic in general, such as truth tables. Uh, right here you have in front of me a simple logic gate that is different than most Minecraft logic gates. Now the reason it's different than most Minecraft logic gates is because this one's used to represent real logic gates used in real life. In real life you have currents that can be sent to ground, whereas in Minecraft you don't need to worry about things like that. Also, uh, resistance and stuff like that is not accounted for in Minecraft, and so such things like that you couldn't really interpret onto an actual circuit board. And remember, since my intent is to show you how to do things in real life as well as in Minecraft, I guess the first best example would be to show you a video where the logic gate is a real life example. So if we look here closely, you'll see that we have a power source and we have another power source. And these two power sources connect to the same wire that gives to a single output. To the sides of these you have two sticky pistons, and what happens is when you activate a sticky piston, it comes in and it terminates this power. In essence, what this is doing is it's sending it to ground. It's stopping the current from passing through the wire because there is a more likely chance or an easier chance for the electricity to go to a source that will more willingly accept it, such as the ground, since it's an infinite energy suction. I guess it sucks out energy at an infinite rate. At not an infinite rate, sorry, at a uh, assumable infinite rate. You assume a lot of things in math. And so you notice that by turning off one of these, though this power source is now sent to ground, this power source is still active, and so as such does not send power to, or as such still sends power to this wire here. If you were to put a light source here, you would notice that it is still active. If we do the same to the other one, the same effect happens, whereas this power source is still sending power. But what happens if you signal both? When both power sources are sent to ground, your output is terminated because it no longer has power to be received from any source. And we have effectively produced a NAND gate. What a NAND gate is it is a gate that requires two inputs and turns them into an output of the opposite input. So if both inputs are on, the output's off. If one input's on, the output's still on because you still have that one power source. If the other output is still on, the input is on, or the output is on, sorry, because you still have this power source. But when both are on, the output's off. Now this brings you to probably the most important logic gate there is. The NAND gate in normal circuits is the most important logic gate, simply because you can build any other logic gate from this gate. And I'll show you guys how to do that in the links that I'm going to set up for this. I've found a perfect website that explains this very, very well. It describes how to build other logic gates from a NAND gate. For example, maybe you want to build an inverter. And what an inverter does is in Minecraft, again, because this is a lot simpler, you don't need to worry about grounding. An inverter it takes your input and it turns it into the opposite output. Right, so when this is on, that's off. When this is off, that is on. It inverts it. It turns it upside down, I guess is what you could say. Oops. So to build an inverter, for example, you would just simply take both these wires and you would hook them together. So now notice I only have one input, and when I turn it on, the output's off. So that's just an example of how you would take a NAND gate and you could turn it into any other logic gate. Next thing I guess I should show you guys is truth tables. Now what truth tables are is they are a representation of what this is over here. It says that here's your input A, here's your input B, and here's your output. And so if both input A and input B are on, what do you get? You get an off. If input A is off and input B is on, what do you get? You get an off. Oh, I guess this is backwards. Sorry, this would be like this. You get on. Off. Sorry. And on. So let's kind of show. Both of these are off. So if input A is off, input B is off. Look at the light source, it's on. If we turn the left one on, which is the next one, left one's on, right one's off, the input is still on. If we turn just the right one on, input B is on, input A is off, output is still on. But if we turn both of them on, output is off, just like there. Give me a second here. So this is a representation using a truth table of a NAND gate. You can also use this for other gates, and it's more of a kind of quick guide as to see what you want your inputs and outputs to do, right? So seeing as how this is the ultimate 1 and the ultimate 0, right? Because if there's 2 inputs, you can only have 4 combinations of inputs, right? You can have on, off, or off, 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 on, off, and on. Those are the only 4 possible combinations with 2 inputs. And so this one's ultimate 0 because both are off, and this one's ultimate on because both are on. If you had 3 inputs, you would technically have, I believe, 9 different combinations, but you would still have an ultimate on and an ultimate off where all 3 are off and all 3 are on. So I guess we'll give you a little bit of practice with this when we move on to actual logic gates. And so I have here an array of logic gates that are used in Minecraft most frequently. You probably, in the creation of a computer or calculator, for example, will use much more advanced logic gates. But as we get to those, I'll show them now because I don't really want to overwhelm you guys. This is pretty overwhelming, but again, I'm going to add a link that shows you a quick reference guide of how to build every one of these. So an input-output gate. Basically, when your input's on, your output is on. That's pretty straightforward. The truth table for that, because it's only one input, it'll only have two. It'll only have 2 possible combinations, on and off, 2 states. So when it's on, the output's on, and when it's off, the output's off. So the truth table for this looks like this, where it's just 1, 0, 1, 0. Moving on, we have our NOT gate. And basically, this is an N stands for inverted. Inverted, or I guess just not. N stands for not. Let's say that. N stands for not. NOT gate. When your input's on, your output is off. When your input's off, your output is on. So the logic, or the truth table for this is exactly similar to the input-output gate, except that it's inverted. When this one's on, this one's off. So this is the truth table for a NOT gate. Moving on, we have an AND gate. Now remember, this one over here is the NAND gate because it is the NOT of the AND gate. The NOT of the AND gate. What the AND gate does is when one input's on, nothing. When the other input's on, nothing. But when both inputs are on, the output is also on. And so the truth table for this, going back to our ultimate 0 and ultimate 1, if both inputs are on, what is the output? It's on. If one input is off, one input is on, what is the output? Off. Same. And same. Now, as I said, this is exactly like the NAND gate, except inverted, right? So the NAND gate is the same outputs, but inverted. So it would be like this. Basically, when you invert something on a truth table, you take all its on values in the output section and you turn them off. And you take all its off values in the output section and you turn them on. And so this would be a NAND gate because, as we've said, when both inputs are on, it's off. as shown, and any other combination would result in it being on. Which brings you to the next point. You can take any gate, any logic gate, and turn it into an invert of itself. So an AND inverts and get the exact invert of the outputs by simply adding a NOT gate to it. And so how that would be done is you could just go like this. Remember, here's our NOT gate. It's just a block with an inverter on it. So we put a block, inverter on it, and we now have our NOT gate, or our NAND gate, sorry. Where when both are on, it's off, on, and on. And that's how you invert basically any output from any logic gate. I'm just going to set these all to on to show which ones I've done. Next, we come across our OR gate. And what an OR gate is that when one or the other is on, the signal is on. Even if both are on, because then one or the other is on, the signal is on. Now, because I put a block here, I had to invert it. On the link I give you, it's slightly different, but that's only because that it actually has the power sources on the block itself. Whoops. And so doing that, you don't need to invert it. You would just leave it. As you can see here. But because I decided to use the switches off the actual block, since they power this block, when turned on, the power doesn't transfer through. But what it does do is it powers this inverter and turns it off. And so I've just taken that and then inverted that symbol or signal to make up for this inverter, and we have our OR gate. And the truth table for an OR gate is as such. When both are on, it is on. When one's on, it's on. When the other's on, it's on. And when both are off, it's off. Now, what would a NOR gate look like? Well, it would do the same thing where we take our outputs and we invert them. So on becomes off and off becomes on. And this is now what a NOR gate would look like. And you could do that by inverting it again or removing one of the inverts I've already added. Moving on, we have our XOR gate. And what an XOR gate does is it's called exclusively OR. So what that means is it only allows OR gates through. If you turn both of them on, you don't get an output. And that's because it's only ORs. You can only have one or the other, exclusively that. You can't have both. If one's on, it's on. If the other's on, it's on. But if both are off, it's off. And if both are on, it's off. It's only a one or the other. And this is really helpful if you want to kind of exclusively choose your outputs, right? So say you have two inputs coming in, but you only want one of them to be active. This is actually how you make adders, is you put you use XOR gates, because if both are on, your output would carry to add to the next column. So this one couldn't be on because you'd have to carry it, so it would have to turn off. So if both are on, it carries and that turns off. That's just an example. So a XOR gate's truth table looks like this. Because only one or the other is on. If both are on, or if both are off, it's off. And a N XOR gate, or a not XOR gate, is the exact same except inverted. So all your offs become on, and all your ons become off. And inverting it would get you this truth table. And you can start to see how this is helpful in that if you make the truth tables, you can see which combinations of inputs would give you your certain output. So you can kind of program your logic gate, I guess, or you can program circuits to using logic gates to get specific outputs. Moving on, we have our 5 o'clock or a clock. It's a 5 o'clock pulsar, I guess it's technically called, but it's also used as a clock. Now what this is it is something that continually pulses at an even rate. So you can go off, on, off, on, off, on, off, on. Right here, you can see that it's at even intervals, or at regular intervals, I guess is a better word. It pulses. And this is used because in programming you'll find later that it actually needs to clock in order to determine the order of programs in which you run things. That's pretty complicated to understand right now, so this is really only a show of what it does. There are no inputs on it, however you could technically put an input on it and that would stop the clock, because you're saying no matter what this input is, you forcefully turned the block on. So even when that's off, it forces it to be on. Right? And the same thing can be done instead of with blocks, just repeaters. I don't think the repeaters is on the link I'm going to give you, which is what I'm going to show you. But it basically does the same thing, except you need to actually turn it on yourself with a pulse. I don't recommend using this one for redstone circuits, simply because you have to, when you turn it on, you can't just leave it on and then turn it off, because it doesn't pulse. You have to, sorry, let me get this back to the off state. You actually have to pulse it really quickly, just like that. Which, if you're gonna make a pulse to pulse this, you already have this, because this is a pulsar. It pulses signals, right? And as I said, on, off, on, off. So you would just be making redundancies in this. Over here we have a faster pulsar, because in Minecraft what happens is if your pulse is too fast, it shorts the circuit and stops it. That's just to stop CPU of your computer from overloading itself and effectively crashing the program itself of Minecraft. So the pulsar is just built like this. There is no on-off switch on it, though again you can make one where it forces it on. There's no way to force this off, I don't think, because as soon as you turn it off, it just pulses. And so it'll pulse forever and ever. This is the fastest you can get it to tick. Ticking is referred to as the pulse, so it ticks every X seconds. This pulsar is the fastest you can get a tick to occur in Minecraft without actually crashing or destroying the circuit itself. I will show you, I guess, really quickly here what it looks like to crash a circuit. Oh, that wasn't it. Basically, this is ticking too fast, and see, it'll eventually crash. See how it keeps blanking out like that? That's it crashing and resetting itself, which makes for irregular intervals. And you don't, when you're programming using a computer, you don't want that. That'll screw up timing and everything. Moving on to the final logic gate, you have your RS NOR latch. What an RS NOR latch is it is a form of memory. You have an input, or you have technically two outputs, I guess. Output 1 and output 2. And your input stores the input into this output and takes it away from this one. Now why is this defined as memory? Is because once you have it saved like that, even if you turn this off, the pulse is saved to this wire, right? So it will always be on. So thus you have memory. If you have 100 of these in a row, you can program it to 100 binary decimal places, and then no matter what you change after that, it will always forever display that original input that you put in. And that's really cool, except it's not helpful unless you can rewrite data, right? So on an RS NOR latch, you have a reset button, which resets it back to its programmable state, which you can then reprogram again. And if you always want this to be 0, you can simply use this as your input instead. Right? Seeing as how they're basically opposites of each other. This one forces this one on, and this one forces this one on. So those are the basic logic gates. Again, I don't want to show you how to build them. I just want to kind of explain what they are and how they work. If you have any questions, feel free to message me, or again, even Benny's Cube, he's probably a lot better at this than I would be and would be way more capable of answering it. So yeah, until the next video, I will see you guys later.